All right, so our next topic we're going to look at is with limits, is we're going to look at what happens when x approaches infinity. So on our previous one, we looked at what happens when x approaches some specific value, like 2 or -5 or something along those lines. Remember, we had a couple different scenarios. We had it where we possibly got just a value for continuous limits. We got something that was a nice value, like if I gave you something like limit as x approaches 4, and we had something like x squared minus 3, we could just plug the value in. So 4 squared is 16, take away 3 would be 13. So in this case, the 4, 13 gave us an actual x and y coordinate, so that was our continuous limits. Then we examined what happens when they were discontinuous. So that's when we had something like limit as x approaches 1, we had something like x squared minus 1 over x minus 1, and when we tried to plug it in, we got 0 over 0. And that's where the problem started. So continuous limits, generally pretty simple. Discontinuous limits, that's the more challenging ones where we had to do some algebra to try to simplify it. And if you remember, those gave us typically our locations of our points of discontinuity. So when you're dealing with discontinuous or continuous limits, it's really the zeros that are the problem. So if we got a nice number like 13, we were done. If we plug something in and we got something like 0 over 4, that's still okay. That's still a continuous limit because that would simplify to 0. So that one was all right. If we got it something the other way around, so if I suppose we had something like 5 divided by 0, we looked at one of those on the previous example where we had something over 0. That one, no matter what we do, we can't get it to work. So we just basically, if you remember that anything divided by 0 doesn't work, just say that it has no limit or does not exist is good enough for now. And then our last type is like the one I had above. 0 over 0 typically meant that we had to do more work, so we would factor it and then simplify it down. So in this case, if we factored the top, we would have got x plus 1, x minus 1. And on the bottom, the x minus 1 was already there, so that would have canceled. Now if we plug in a 1, we would have got a limit of 2. So the 0 over 0 means we got more work to do. 0 divided by 4 was just 0. 5 divided by 0 was no limit. So those were kind of the types that we've looked at so far. So today's, what we're going to do is go one step further, is what happens when the limit number now is no longer just a regular integer or fraction or decimal or something like that. What happens when it's infinity or even negative infinity? So these infinite limits kind of work a little bit differently. So if we tried the same strategy on this title page, if we plugged infinity in, you'd get infinity cubed on the top minus 2 times infinity, and then on the bottom we'd have 4 times infinity squared plus 1. So what does that tell us? It's sort of like saying we got infinity divided by infinity. So it's very similar to when we had 0 over 0. 0 over 0 meant we had to do more work to try to actually figure out what that limit was. When we get things like infinity over infinity, same thing. We have to do some more work to try to figure out what that will actually mean. It's not going to equal 1. Maybe it equals 0. Maybe it equals 2. Maybe it equals 50. Who knows? So that's what we're going to be looking at today. So for this first part, this is kind of what just summary of what we just looked at for some examples. So step 1 in our first limit video was plug in the limit value. If it works, it's continuous, and that limit you figured out was the y coordinate. So plug it in and get a value is always our easiest step, but it's one that we have to do, otherwise we're not really sure what our next step should be. Step 2, what we looked at yesterday, was if you plug it in and you get something like 0 over 0, then we got to do more work. So like I just said on the previous page, if you plug it in and you get something like 0 over 4, that's okay, that gives us a 0. If we got something like 5 divided by 0, then we just say we have no limit, and that's also okay. So the only scenario that we sort of have to worry about is when we get 0 over 0, and that's where we factored, rationalized, used common denominators, something like that. And in those cases, that gave us the point discontinuity. So far we've looked at what happens when we have a y-coordinate limit, or what happens when we have a point to discontinuity type limit. So today's stuff now is what happens when we get infinite values. So before we look at a strategy, there's 2 infinite limit laws that we take advantage of in this case. So the first one is if you have 1 divided by infinity, that gives us 0. right? So if we actually were to plug infinity into this equation, 1 divided by infinity, well, what's 1 divided by infinity? Well, we can't do it, but if you type in 1 divided by a really, really big number, then you'll get approximately 0. And eventually, as the bigger that number gets, the closer and closer it's going to be to 0. So that's just one very handy one that we like to use to help us solve these infinite limit questions. If we can change it to look something like that, it makes the question really easy, because then we get zeros for any of those locations. So for this first one, we have 3n minus 2 over n. So if we tried to plug infinity in again, we'd get something like infinity over infinity, which doesn't work. So we're going to have to do some sort of simplifying. So if you remember from fractions, if you have a fraction divided by a value like it's written here, we could actually split that apart. So we could change this to be 3n over n, and then the second part we could write it as 2 over n. So instead of having it as a common denominator, we could break them back apart. So now, if we were to plug infinity in, the first part's a problem, but the second part is okay. So just like we did with factoring, before we get to that, let's cancel out the n's. We have 1 on the top and the bottom. So now our limit would just be 3 minus 2 over n. So the 3 is good. Limit of 3 is just 3. The 2 over n ends up being just like what our limit law is in the box. Whether it's a 1 or a 2 really doesn't matter. 1 divided by a really big number is going to be 0. 2 divided by a really big number is also going to be 0. So this will then just simplify to be 3 minus 0, which would just give us 3. So for this first example, limit of 3n minus 2 over n is 3. That's our final answer. Okay. The second limit law that's on this page looks a little different, but it works pretty much the same thing. What this one is saying is, what's the limit as r approaches n? And if r is a fraction, the way it's written here, it says r is absolute value of r is less than 1. So that means r is got to be a decimal or a fraction. So if you do a fraction like 1/2, 1/2 to the power of 4, something like that, or 5, right? That fraction gets smaller. So 1/2 to the power of 5 is 1 over 32. So it works pretty much the same. It's just we're kind of thinking of it as the base number being a fraction instead of the equation being a fraction. But they're identically the same logic. So if you see something written as r to the n where r is a fraction, you could just think of it as 1/2 to the n, which would then be the same thing as 1 over 2 to the n. And you can see it's pretty much identical to this exact same formula. And if you're not sure, you could always just plug it in on your calculator too. So for this first example, if we try plugging in a infinity, so you'd have 0.4 to the infinity, put that on your calculator, put 0.4 to some really, really big number, that's going to give you the value of 0. So here we'd have 4 times 0, which would simplify to, oops, not 4, it would simplify to 0. Anything times 0 is 0. So for this first one, our limit was 3. For the second one, we're getting a limit of 0. And that's basically the two limit laws. What we're going to do now is let's figure out a more efficient way of working with these. Alright, so for our last strategy that we're going to look at today, so our first strategy was plug it in. If it works, great. Second strategy is plug it in. If we get zeros involved, zeros on top, we're okay. Zeros on the bottom, we're okay. But if we get 0 over 0, it's undefined. Now what we're looking at is what happens when we plug it in and we get something like infinity over infinity. And that's pretty much also undefined. We have to do more work. So what we're trying to do is use this 1 over n equals 0 limit law when n approaches infinity. So what we're going to do, instead of trying to use the strategies that we just used, a simple one that we do is we just basically divide everything by the highest power. So for this first one, you can see our highest power in the equation is just x, or x to the 1. So what we would basically do is rewrite this question to be x over x for the first term, 4 over x for the second term, and then on the bottom we have x over x as well. So as long as you divide everything by the exact same power, we're not changing the equation. Now when we simplify it, x over x cancels on the top, also cancels on the bottom. So those would simplify to just be 1s. So this whole equation would simplify to be 1 plus 4 over x over 1. And now we can use this limit idea. So the 4 over x part is just going to become a 0, right? Because that's using our limit law. So we end up just getting 1 plus 0 over 1, which would be 1 over 1, which just gives us 1. So in this case, our limit as x approaches infinity is 1. Let's try it one more time using the same sort of idea. So for this next example, you can see our highest power is x cubed. So if we rewrite the entire question as dividing everything by x cubed, so it takes a bit of time to write this step, and we're going to show you in a sec we don't really need to write it. We'll understand a shortcut here in a second. But if we divide everything by x cubed, we get a whole bunch of fractions. Some of them will simplify. So again, the first one you can see x cubed over x cubed would simplify, so that gives us 3. For the second one we have an x squared on top, so that cancel out with the x cubed on the bottom, so we'll just get 2 divided by x. But again, using our limit rule, 2 over infinity would be 0. For the last one we have 5 over x cubed. Whether that bottom is an x squared, an x cubed, doesn't really matter. It's still going to be the same law, because 5 divided by infinity cubed is still going to be the same thing as 1 over infinity. It just gets even bigger faster, so that would be a 0. And then on the bottom, our x cubes cancel again, so we get a 2. And then the other 2 would be very similar to the previous 2. So one of the x's would cancel, so we'd have 3 over x squared, which would become a 0. 4 over x cubed is also 0. So all of this simplifies down to just 3/2. So that's it for dealing with infinite limits. We're basically just dividing by the highest power. If you remember back in Math 30, when we were dealing with horizontal asymptotes, we used sort of a shortcut strategy, which was divide the coefficients of the highest powers. As long as they're the same power, you could divide those coefficients, and that gave us the horizontal asymptote. And you can see with this last example, we're doing exactly the same thing. So this 3/2 that we got as a limit, really what that's telling us is what is the horizontal asymptote. So remember when we had 0 over 0, that limit kind of gave us the point of discontinuity. In this case, we're determining the horizontal asymptotes. So infinite limits really are another way of saying what are the horizontal asymptotes. So we can go back and use that highest power trick. It's a lot faster. So if we did that on the first one, you can see we'd have 1 over 1. We got our answer of 1, which was good. If we apply this strategy to this last example, you can see it'll work a little bit faster because we have 7x to the 4th on the top. We have no x to the 4th on the bottom. So we could think of it as 0x to the 4th. So 7 divided by 0 is undefined. So that means this one has no limit. So from a graphing perspective, that means this one would have no horizontal asymptote. And that's it. So that's where we're going to stop with the algebra for limits, and then we will, our next lesson was we're going to look at more from a graphing perspective what's going on with limits.